Well, folks, the very, very last day of content for us. So, wow, you guys have worked hard. It's been a good year. I'm super proud of you. And let's just finish this through to the end here. And so today we're going to talk about electric power. Electric power like what comes to your house, kind of electric power. Obviously it comes to your house as alternating current, but the way it's measured is the same either way. So the definition of power is just the same as the definition we used back in chapter 8, where it is the rate at which electric energy is used. Now, the units for this are going to be, so that's why we've got power is equal to the rate, it's over time, that electric energy is being used. The units for this are going to be joules per second, which is equal to, you remember your definition from chapter 8, it's equal to a watt. But if I want to redefine joule as in this context, then getting joule all alone, I would move this over and this becomes a joule is a watt second. A joule is a watt second. Now, if I look at my equation, P is equal to delta PEQ. Delta PEQ is also QV. Delta PEQ is QV, that was from the last chapter, over time. And stop for a moment and think. Q over T is the definition of what? It's the definition of current. So it's also P is equal to I, Q over T is I, V. Now if P is equal to IV, we just showed that. P is equal to delta QV over T, delta Q over T is I, the V remains, so P is equal to IV. But I also know that V is equal to IR. So now I can write this because I have a way of putting all of these terms together. I can also write P in terms of resistance. So I want an equation that has V with R, V with I already have, and also I with R. So if that's the case, then if V is equal to IR, then wherever I see an I can put, wherever I see a V, I can put an IR. So P is equal to IV becomes P is equal to I, and then V is equal to IR, so V is equal to IR. So P is equal to I squared R. But also I know that if V is equal to IR, I is equal to V over R. So P again is equal to IV, but in place of I, I'm now going to put V over R. So P is equal to V over R, which is my I, times V. So P is equal to V squared over R. And just a reminder that P stands for power. And power is written in watts. I is current. And current's units are amps. V is potential difference. And the unit for that is volts. And R stands for resistance. And the units for resistance are ohms. All right, so we've gotten a lot of new things thrown at us this chapter, and so I'm kind of belaboring this a little bit just so that you're constantly being reminded what these things are. So let's work through this. A man holds the leads of a 100 volt source of EMF in his hand, causing 10 milliamps. Remember that if there's a letter in front of the unit, it's a prefix for for metric conversions. That's milliamps of current to flow through his body. What is the resistance of his body? At what rate is electric energy converted to other forms? And what is the total amount of energy converted in 30 seconds? So let's figure out what we know and what we're looking for. So this is one of those times where it's really useful to write down what you know and what you're looking for along the side. So I have this, so my potential difference, my V, is 100 volts. And then my current, which is I, is equal to 10, and then the milli means 10 to the negative 3 amps. And then finally, I'm looking for resistance. So do I have an equation that accommodates V and I and R? That's Ohm's law. V equals IR. So 100 is equal to 10 times 10 to the negative 3 times R. And R then is going to be equal to 10,000 ohms. Right, now the next question is, at what rate is electric energy converted to other forms? So if I'm talking about the rate of utilizing energy, that's power. So power is, I don't know, that's what I'm looking for. I know that I know V, I know I, and now I know R. I can use any of that. I'm going to use P is equal to IV, which is equal to 10 times 10 to the negative 3, because that's what I had over here. But again, I could have used P is equal to I squared R. I could have used P is equal to V squared over R. This one's just easier. Times 100. So it's 1 watt when I do the math. Now it's saying what is the total amount of energy converted in 30 seconds. So I also know that P is equal to any change in energy. In this case, it's delta PEQ, but it's any change in energy over time. So it's going to be 1 is equal to delta PEQ over 30. So my energy, and in this case again, is delta PEQ, is equal to 30, and the unit for energy is joules. Okay, again, I've got so many equations. I want to write down what I'm working with so I know what equation is best. The power company charges their customers according to the amount of electrical potential energy the customer uses each month, delta PEQ. But instead of charging by the joule, the company charges by a unit called the kilowatt hour. A kilowatt hour is the energy expended when a device converts electric potential energy to other forms at a rate of 1,000 watts a kilowatt for a time of 1 hour. The conversion of kilowatt hours to joules is, so you can see back and forth. I will tell you the reason that they do this is because if they did the number of joules, it would be gargantuan number. Let me show you. So we're going to convert 1 kilowatt hour to a joule. And you remember that we said the joule in terms of these kinds of units is the same as a watt times a second as opposed to a kilowatt times an hour. So what I need to do is convert my kilowatts to watts, my hours to seconds, and then I will have the number of joules. So let's set it up as dimensional analysis. So I have my kilowatt hour, and first thing I'm going to get rid of is the kilowatt. That was a nice straight line, is the kilowatt. And so 1 kilowatt is 1,000 watts. So that's going to get rid of the kilowatt and the kilowatt. And that leaves me with watts. And now I have to convert hours to seconds. And we know that 1 hour is 60 minutes times 60 seconds in a minute. So it's 60 times 60, or 3,600 seconds. And when I multiply it all out, I'm left with 3.6 times 10 to the 6th watt times second, because they're next to each other, not over each other, which we know is the definition of a joule. So it's 3.6, or it's equivalent to a joule, I should say. 3.6 times 10 to the 6th joules. Calculate the cost to operate a 120 watt light bulb if electricity costs 8 cents per kilowatt hour. So in order to use my 8 cents, everything has to be in kilowatt and hour. My time is in hour, so I'm good with that. My time is an hour, but I need to convert my watts to kilowatts. So let me take care of that quickly. So 120 watts is equal to 0.12 kilowatts. And I already have it in 24 hours. So in kilowatt hours, it's 0.12 kilowatts times, because that's what actually is built into the kilowatt hour, times 24 hours. So the answer for that is going to be 2.88 kilowatt hours. And then it's 23 cents per kilowatt hour. So I'm going to multiply this by, it's 8 cents per kilowatt hour. So I'm going to multiply it by 0.08. And I end up with a cost of 23 cents. And that's it. Not with a bang, but a whimper. It goes out with not a bang, but a whimper. Our year does. All right, folks, your homework is 26 through 36, but not number 35. 26 through 36, except number 35. All right, let me know what